So, let us proceed today for our 25th lecture on transport phenomena. In this, we will start the conductive heat transfer. Conductive heat transfer. As I have told you that there are three modes of heat transfer: conductive mode, convective mode, and the radiation mode. So far as this radiation mode is concerned, I have covered up in the previous classes by arriving the concepts of black body radiation, concepts regarding the components of the various radiation impinging on a surface. Also, we have discussed the radiation shape factor, a factor which determines the fact that how much energy from a radiating surface or from a radiating body will be received by the receiving surface. So, that quantity is determined by the radiation shape factor. I have also discussed the radiation shape factor problems in some of the simple geometrical cases. Now, from today we will start the subject matter of this conductive heat transfer. So, basically due to an existing temperature gradient, due to an existing temperature gradient, due to an existing temperature gradient in a body, transfer of energy takes place transfer of heat energy, you can say here, transfer of heat energy takes place from a higher temperature region to a lower one. So, if you are talking about the transfer of energy from the one region to the another one, the very characteristic feature that these two regions have, that there is a difference in the temperature between these 2 points or between these two regions, by the virtue of which a temperature gradient exists, and due to this existence of this temperature gradient or temperature difference, you can say the transfer of energy takes place. The rate of heat energy transfer per unit area is proportional to the normal temperature gradient, That means, if I am assuming that the Q is the amount of heat energy transferred per unit time, then it can be said that Q by A is directly proportional to day by T by day by X, or you can say Q by A, that will be equal to minus into constant of proportionality K day by T by day by X, or Q equal to minus K day by t by day by x, it may be written as k dt by dx. If I am assuming that the t, which is a function of spatial coordinates and time, and if I am considering the x direction only, then the partial derivative of temperature with respect to x may be regarded as the normal derivative of temperature with respect to x. So, in this, let it be question number 1 here. U is the heat transfer rate, K is the thermal conductivity, K is the thermal conductivity, day by t by day by x, or you can say dt upon dx is the temperature gradient. Temperature gradient. Here, in order to bring the importance of the negative sign here, it can be said that the negative sign is in accordance with the second law of thermodynamics, is in accordance with the second law of thermodynamics, that heat must flow downhill a temperature scale. In accordance with the second law of thermodynamics, that is, heat must flow downhill a temperature scale, must flow downhill on a temperature scale. This is the most fundamental equation of the conductive heat transfer, and it is also called sometimes it is usually called as the Fourier law of heat conduction. So, equation number 1, it is called the Fourier law of heat conduction. Here, first important quantity which often comes in the various cases of heat transfer is the thermal conductivity. So, our next task should be how this thermal conductivity can be defined. So, taking the equation number 1, here, so you can easily elucidate that what should be the definition of K. So, the thermal conductivity, it is defined as amount of heat energy transferred per unit area of a material under unit temperature gradient. Material under unit temperature gradient. If you would like to have a genesis of that from where such a definition can be arrived, that you can take the relevance of the equation number 1, that is q is equal to minus k a into dt by dx. Here if area is equal to 1, if A is equal to 1 and dt by dx, that is the unit temperature gradient, that is equal to 1, then you can say that q is equal to minus k. So, what you can see, that the amount of heat energy transferred this per unit area, because I have taken the area is equal to 1 here. So, even if you are not taking the area is equal to 1, then if you are defining the q by A is equal to minus k, then in that case also the amount of heat energy transferred per unit area of the material under unit temperature gradient. This is the definition of the thermal conductivity of a material. Now, expression for k can be given from here, from the equation number 1, that will be equal to minus q by A this. So, the dimensionally that is equal to q upon t, dimension of this q, that is the amount of heat energy transferred per unit time, that is q upon t. The dimension of area is L square. One by dt by dx, that is equal to dx by dt. In principle, it does not happen in the case of differential, but here L upon t. So, the dimension will be q t raised to the power minus 1, L raised to the power minus 1, t raised to the power minus 1. This is the dimension of the thermal conductivity. So, the SI unit of this thermal conductivity, SI unit of this thermal conductivity, that will be equal to joule per second per meter per Kelvin. This is our SI unit for this thermal conductivity, and the CGS unit, and CGS unit is equal to calorie per second per centimeter degree centigrade raised to the power minus 1. This is calorie, don't get confused. So, these are the SI and the CGS units of this thermal conductivity. Another important quantity which often comes in the heat transfer study is the thermal diffusivity. Especially being the student of the metallurgical engineering, you must have the idea about the various metal processing industry, metal processing techniques, out of which the 70 to 80% processes are related with the solidification processes, that is the casting technology. Now, the behavior of the liquid metals and alloy, once it is allowed to solidify in a mold, then the very characteristic of the mold will regulate the entire property in the metal or alloy which has been solidified in that particular mold material. Why? This is because of the fact that the thermal conductivity, the thermal diffusivity, the specific heat capacity of the mold material at constant pressure, these are the factors which influence that how far the mold material is able to absorb the heat energy of the liquid metal. Once you have poured the liquid metal in a mold, it means it has certain amount of associated energy which have been achieved by the liquid metal during its course of melting. So, that heat energy needs to be dissipated in order to get it solidified. So, depending upon the mold material you have chosen and its thermal diffusivity value, the amount of undercooling which will be experienced by the liquid metal during the course of the solidification will be different. At a higher undercooling, there is a possibility that the more and more particles will get nucleated from that liquid metal, and if I am considering a specific volume, and in a specific volume if there are so many grains which can be nucleated, so the space available for each and every nucleated grain will be confined to some extent. Under these circumstances, the metals or alloys which have been solidified in the particular mold material, if the rate of nucleation is high, and subsequently as a result of that, if growth rate can be suppressed or growth rate can be restricted, a finer grain in the microstructure may result. This gives rise to an enhancement in the mechanical property of the alloy, and also on the other hand you can say that you can tailor the mechanical property as well as macrostructure of the material which you are going to solidify by having a proper choice of the mold material, by having a proper choice of the superheat which have been given to the liquid metal in order to get it melted. And how the superheat can be defined? The superheat is defined as the temperature, margin of the temperature through which you have increased the temperature during the course of melting. Let us suppose the aluminum silicon alloy, let us suppose it is melting at 675 degrees centigrade. If you are carrying out the melting process to 715 degrees centigrade or 700 degrees centigrade, it means you have given respectively a superheating of 35 degrees centigrade and 25 degrees centigrade. So, that proper choice of mold material as well as a proper choice of the superheating of the material can easily dictate the property in that particular metal or alloy which is desirable. So, the next important quantity is thermal diffusivity. Next quantity is thermal diffusivity. So, the next quantity is thermal diffusivity. Important parameter is the solidification of metals and alloys, or you can say the casting. Solidification and alloys, it is defined as heat absorbing ability of the material. And mathematically we can say, this quantity which is denoted by the letter alpha, the thermal diffusivity is defined as K upon rho Cp. So, if you take the dimension here again, alpha is equal to K upon rho Cp. So, the dimension of K is Q divided by rho ml raised to the power minus 3 into Cp q m raised to the power minus 1 t raised to the power minus 1. So, it will come as L square t raised to the power minus 1. This is the dimension of alpha. So, correspondingly the SI unit of this alpha is meter square per second, whereas its CGS unit is centimeter square per second. This is the thermal diffusivity. Now we have discussed the definition of the thermal conductivity and the thermal diffusivity. As you see here, the thermal diffusivity is nothing but a function of the thermal conductivity of the material and the thermophysical property of the liquid metal which is going to solidify in a particular mold material. So, in a nutshell, you can see that you have to determine the value of K. The value of thermal conductivity needs to be known. Once the value of thermal conductivity is known, then from the handbook you can easily calculate the value of alpha by utilizing the equation alpha is equal to K upon rho Cp. So far as the experimental determination of the thermal conductivity is concerned, it is basically determined by the Searle's method and also the Ingenhousz experiment, by the virtue of which you can determine the value of K. For a practicing engineer, all the time the determination of thermal conductivity by the aforesaid techniques is a quite time consuming task. So, keeping the fact in view that a practicing engineer may not have such an enough time to determine the thermal conductivity of the material by the existing experimental method, some of the correlations have been devised by the scientists. So, our next task is, to which we will go through, is the empirical relationships for the thermal conductivity. This is very important so far as the conductive heat transfer is concerned. So, the next thing is the empirical relationships for conductivity determination. Now, for gases, number 1, empirical relationship means the relationship which is valid for a certain condition. So, the relationships which are valid for a certain condition, that condition which is being self-explanatory in the equation itself, that suppose you have to determine the thermal conductivity in the case of gases, then this is applicable for the gas only. If I am saying that this is for the polyatomic gas, that means that equation holds for the determination of the thermal conductivity for the polyatomic gases only, not for the monoatomic gas. On the same guidelines, the thermal conductivity value for the liquids can be determined by using the empirical relationships, as well as for the solids you can also determine the thermal conductivity by using such empirical relationships. So, we will go through such empirical relationships one by one. First relationship is the kinetic theory of gas formula. Kinetic theory of gas formula. This is the formula is K is equal to Cv V lambda by 3, where Cv is the specific heat capacity at constant volume. Specific heat capacity at constant volume V is the specific volume, that is the volume per unit mass, specific volume, and lambda is the mean free path, mean free path. By having these three different parameters, by having the ideas regarding these three different parameters, you can use the kinetic theory of gas formula as K is equal to CBV into lambda by 3 to determine the thermal conductivity of that particular gas. In the case of dilute gases, that means where a mixture of gases are there, and you have to determine the thermal conductivity of one of the gas of that mixture, which is in the very low concentration. So, in the case of dilute gases, the formula of thermal conductivity is K is equal to 1 by d square Kb cube T divided by pi cube m raised to the power half, where this Kb is the Boltzmann constant. Kb is the Boltzmann's constant. This is defined as R divided by N. The gas constant divided by Avogadro number. T is the temperature in Kelvin scale. D and M are the atomic diameter and mass, atomic dia and mass respectively, and pi is the constant. Another formula is the Chapman and Gauling formula. Another formula is, or equation is, Chapman and Gauling equation. This Chapman and Gauling equation is given as K is equal to 1.987 into 10 raised to the power minus 4 into by m raised to the power half divided by 1 upon sigma square omega k, where this T is absolute temperature, where this T is the absolute temperature, T is the temperature, M is the molecular weight, sigma is the collision diameter, and omega k, this quantity is a function of dimensionless temperature kBT upon epsilon, where kB is the Boltzmann constant and epsilon is the energy term resulting from the interaction between the various atoms. So, in this the description is a dimensionless temperature, and epsilon is the energy parameter, of interaction among molecules of interaction amongst molecules. This is the Chapman and Gauling formula. The third formula is the Eucken formula, which is utilized for the polyatomic gases. So the next formula is Eucken formula for the polyatomic gases. This is Eucken's formula. This is used for polyatomic gases, expressed as the Eucken formula is K is equal to Cp plus 5R divided by 4m into mu. Rm as the usual meaning that I have already said, and mu is the viscosity. These are the empirical relationships which is utilized for the determination of thermal conductivity in the case of gases. Now come for the liquid. For liquids, the important correlationship is the Bridgeman equation. This is used for monoatomic liquid, liquids. This equation, Bridgeman equation, can be expressed as K is equal to 2.5 into n upon V raised to the power 2 by 3 into Kb into Vs. Here n is the Avogadro number. V is the volume per mole. Vs is the velocity. In the liquid. This velocity of sound in the liquid can be determined by the Laplace correction to the Newton's formula. So it can be determined as gamma delta p by delta rho raised to the power half. The quantity here, this quantity delta p by delta rho can be measured or evaluated from isothermal compressibility data. This isothermal compressibility is an important term which we will frequently encounter in the transport phenomena course as well as the transport phenomena practical. This quantity is defined as, this isothermal quantity, a thermodynamic quantity, is defined as beta is equal to minus 1 upon V, delta V upon delta P at constant temperature. That's why it is called isothermal, because the temperature is constant. That means the measure of the volume change with respect to the pressure change and per unit volume. So this quantity is called the isothermal compressibility. It is necessary, and my appeal to you, all of you, that you should remember this formula, that is the formula for isothermal compressibility. Later on, towards the end of the class, we will try to solve a numerical problem related with this equation. So this is all the about for the. Now come to the solids. For solids, for the determination of thermal conductivity through the empirical relationships, in the case of solids, there are two types of relationships. First relationship, that is called the Weidmann-Frange law. Weidmann-Frange law is law which is related with the Lorentz number, and this is given as K is equal to L into Ke into T, where Ke is the electrical conductivity. That once the electrical conductivity is known, the temperature is known, and the quantity L, that is the Lorentz number. If these three quantities are known, then you can easily evaluate the thermal conductivity of the solid. But the condition is that solid must be a conductor of electricity, because unless the material we have the conducting nature, you will not get in data regarding the electrical conductivity. So L into K into T. So K is the electrical conductivity, T is the temperature, definitely that is in the absolute scale, and L is the Lorentz number. In examination, if any numerical problem related with such type of equation will be given for you people to solve, the corresponding data will be given. So Weidmann-Frange law, and second one is the for porous solids such as sponge iron and the various solids which have porosity in their structure. So for porous solids, the formula is effective thermal conductivity, that is equal to Kf raised to the power epsilon Ks raised to the power 1 minus epsilon. In this equation, K effective, Kf and Ks are the thermal conductivities of better to write here effective thermal conductivity, comma thermal conductivity of fluid filling the pores. That means if the material has a porous structure, then the fluid must be there in the pores. So Kf is the thermal conductivity of fluid filling the pores, and thermal conductivity of solid respectively, thermal conductivity of solid respectively. So far as this quantity epsilon is concerned, that is called the void fraction, So these are the empirical relationships which can be utilized for the effective determination or effective evaluation of the thermal conductivity of the metal or alloy or any material in different circumstances in different their respective states. So let us try to go through one numerical problem on the basis of this Bridgeman equation. So numerical problem is example for the Bridgeman equation. Example of Bridgeman equation. Bridgeman equation. Let us suppose you have to evaluate the thermal conductivity of a monoatomic liquid. Of a monoatomic liquid, the data are the density has been given. Let us suppose this is given as 3.9 kilogram per meter cube. Another data which has been given is the value of the isothermal compressibility, that is equal to minus 1 by V delta V by delta P at constant temperature. This data is 2.7 into 10 raised to the power minus 8 per Pascal. The value of Kb, that is the Boltzmann constant, is 1.38 into 10 raised to the power minus 23 joule per mole per Kelvin. That is unit of R, as that is unit of R by N. N is simply a quantity, so this unit joule per mole per Kelvin. The value of gamma, that is the Cp upon question, and the molecular weight has been given as 47 of that liquid. So you have to determine the thermal conductivity of this monoatomic liquid, that what should be its value. See, the problem is itself is a direct application of all the data, but some necessary transformation is required in this formula. That is why I have chosen this example to make you understand how this Bridgeman equation can be used. So, the principal quantity which is to be determined first is the velocity of sound in that particular liquid, that is Vs. Utilizing the Laplace equation here, delta P by delta rho, a whole raised to the power half, that is equal to gamma raised to the power half, and we can write delta rho by delta P raised to the power minus half. Rho is the density, that is density of unit volume, density of unit mass. Here it is necessary to emphasize that here the density rho is defined as 1 upon V. That means volume of unit mass, volume per unit mass, that is called defined. 5 minutes lagi. That is the volume per unit mass, that is equal to, here it is defined as gamma raised to the power half delta by delta P, rho is equal to 1 by V whole raised to the power minus half. It can be further transformed as gamma raised to the power half minus 1 upon V square raised to the power minus half. It can be further written as gamma raised to the power half into 1 by V into minus 1 by V delta B by delta P raised to the power minus half. This quantity is the beta. So, this gamma raised to the power half, this is the rho into this quantity is the beta. As the value of gamma is equal to 1, so Vs can be accordingly written as rho beta raised to the power minus half. Putting all the values from here, you can easily determine the quantity Vs as that. Through calculation you will find this value will be 97 meters per second. Now using the Bridgeman equation, here, that is the k is equal to 2.8 into n by v raised to the power 2 by 3 into the Boltzmann constant into the velocity of sound. So that will be equal to 2.8, and v is the volume per mole. So here you can determine the v, that is the molecular weight, that is given 47 divided by this Avogadro number, sorry, the density 3.9 into 10 power 3, and this will come as n, that is a 6.023 into 10 raised to the power 23 divided by v has the value 47 divided by 3.9 into 10 raised to the power 3 into 2 by 3. The value of kV, that is 1.38 into 10 raised to the power minus 23, and to the velocity of sound, that is you have obtained, that is the 97 meter per second. When you bring all the calculations from the calculator, this k will be evaluated as 5.08 into 10 raised to the power minus 4 joule per meter per second per minute. So this is the procedure where the transformation from here to this, that is the evaluation of this quantity, that is the velocity of sound traveling that through that particular liquid from which thermal conductivity should be determined, that will come as rho beta raised to the power minus half. Thank you.